enough for them, so they keep doing it. They didn't work, so they change their behavior and they do it differently. Okay, so we can program these into these agents, and then you can see how this agent behave according to the feedbacks that the environment is giving to them, and obviously how their behavior affects the environment. Okay? Now, building an APM is not so straightforward. It looks like a game. It's actually fun to play with, especially if you use NetLogo or if you've seen NetLogo. It looks like a video game, more or less. So it's very appealing. However, it's very important for these reasons. It's very, very important to conceptualize the system and to define the purpose or the research question. Without a good research questions, your agent-based model is just a toy. But not a toy model, it's just a toy. So, secondly, it's necessary to find a set of formal specifications that can characterize these conceptual models. And the models need to be coded and implemented. So every agent receives inputs, every agent behaves according to predetermined conditions, and then acts generating new environmental output that becomes the input for the next behavior of the agent. Okay? Is something not clear? Something you want clarification on? Okay. So this is a layout of a simple agent-based model. You have a setup, you have an environment, you have agents that interact between themselves and with the environment. And then you have the stopping conditions, so you decide when to stop your simulations. It can be a time frame, it can be that the forest doesn't exist anymore, or that all the fishes are fish. Or it can be that no one needs to work anymore, because for some weird reasons they don't need to. So, depending on, you can build in all these. And these are examples of agent-based models in logins. And this is an interconnected network that has some adaptive behavior into it. So what happens is that we can set it up, and we can let this little man go and see how fast we clear the forest. And we can also see if we change the number of lumbermen. We can also see a certain pattern, like if we build a mill, most likely all around will be completely empty and the forest will stay at the edges. So we can also visualize it in 2 dimensions. Yeah?
Just explain your decision variables a little bit.
The variables that are here? Okay. We have a number of lumbermen. We have a certain amount of trees that are there in the beginning. We have different species of trees. Now, in this case, every tree has the same value. But you can actually go into the code and just change those values. And so the lumberman will prefer a certain type of tree than another one. So it will love first a certain type of tree, and then it will go on until to the others. And then there is a probability of new tree growing. And we have the value of the forest and the number of trees that are there. So you see, this is not enough to clear the forest. Actually, the forest is growing a lot in the edges and nothing in the center. Because obviously transportation cost plays a role as well, implicitly. Yes?
It might be a complication that you have to put in, but you don't have any density component in terms of where the new tree is going to pop up.
No. Well, actually, the new trees is scattered randomly. The problem is that these lumbermen move so fast that only the trees that are at the edges will remain. And while the trees that are in between, they log very fast.
But if you had some sort of threshold density that the forest could have,
yes, then it would be different.
not represented here.
No, then it would be completely different. But you can, the good things about these models is that you can just add a couple of lines of code and you can just change that and put the density dependence into it.
So that system that you showed me, that's a sustainable system because the profit's going up.
In theory, yes, it is. Well, it depends. But if we then introduce more complexity, like we introduce fire, for example, that's not really sustainable because a lot of forests come together and we need fire lines. We know that. But in theory, it is sustainable. It's a toy model. But it gives you an idea of what agent-based models can do and why I think they're actually appropriate somehow in certain conditions to represent interaction between human and environment or a couple of social ecological systems. Obviously, it's not the only instrument. It's this, and it has to be. We need to have multi-methods approaches anyway as well. So different types of modeling, different types of techniques, and also case studies, experiments, pilots. Because the systems we're dealing with are really complex, and we don't really understand enough on how the For certain things we have a good understanding. But when we couple them together, we still don't have an in-depth understanding of what might happen or how we can change the trajectory that we are in right now. And I show you, this one is another very simple. This is an interdependent network. So I don't know if you're familiar with networks, what we'll talk about on Thursday. Basically here it's very simply done. The red nodes represent social entities, white ecological entities. They're not defined, it's just an entity. They don't have any properties, they just have links. They're linked to each other. They're linked to each other only if they're dependent on each other. So we have ecological nodes dependent on ecological nodes, social nodes dependent on ecological nodes, social nodes dependent on social nodes because of trade or other things. And I can let this go. We can see different types of robustness of the system depending on the adaptability of the two systems. Now here adaptability is very easily defined as the ability to rewire your own edge or reattach yourself to an ecological node because you need to learn resources. That's for the social system. And for the ecological system is the ability or the probability for them to attach to another ecological node. Because here in this case is assuming that you need at least two connected ecological nodes to function. And you can switch, you can change those parameters as well. And the results of an agent-based model are also a bit different. They generate time series in most cases. The results are often analyzed using advanced statistical techniques. Though the good thing is that since the data are more or less clean, it's easier to use statistical techniques on agent-based models rather than on actual data somehow. Though sometimes it's not so easy, but most cases. And a single simulation run is just a particular case in the parameter space. So we need to have a lot more. We can't simulate something one time because all the outcomes are probabilistics. So we have a mean outcome at the end of the day. We don't have a specific outcome. If we have the same initial condition, we might arrive at two completely different scenarios, even with the same initial conditions. And if they vary slightly, they vary a lot because of the old probability, because most of the actions that we undertake are based on probabilities. Okay? And there is a random number generator. Obviously, if you have the same initial condition and you have the same random number generation, then the results will be the same. But if one of the two things are missing, then they will not.
But in this case, the random number is representing the assortment.
Yeah, it's the random seed, basically because all the simulation computers, they're not very really random, they're semi-random. So what happens is that the computer has a seed in which it has inbuilt a certain sequence of numbers that comes out.
But is that supposed to represent the perturbation to the system, or is it their behavior?
Is that since we don't know exactly how people behave, then it's better to have a spectrum. That's why we use probability. And that's why we don't fix those probability all the time. So we know that if that is the probability that a person, or that is the distribution of behaviors that we have of a specific person, of a specific management, then these are the most likely outcomes under these conditions.
You can't take cultures and norms and punishments and make it,
Yes.
make it more deterministic.
Yes, you can. But I don't want to, but you can. And sometimes it's actually easier. Sometimes you can go on, make it deterministic, and then start building probabilities into it. That's actually the best way to do it, so you really understand all the functional processes that are going on into building these models. That's why it's very important to keep it simple and stupid, like this. And you need to really put a lot of thoughts in understanding and planning how single agents will behave. So the choice of rules actually are what is what shapes the model at the end of the day. So that is very important that those rules are grounded either in empirical results or in the literature. So you can't come up with anything and just play with it. Okay? And then you have a continuous in theory, the best way to build these models is a continuous interaction and feedbacks between researchers and experts. So that it's possible to shed light to the appropriate parameter space region we want to explore and to assess the appropriateness of the model in its different stages And still, we risk to have errors in artifacts. Now, an error is if I code something, I want that A happens before B, but what I actually do is that B happens before A. And I don't realize it. And in artifacts, yes? Okay.
You finish.
And an artifact is that I'm sure that I build the process in a certain way, but actually the process is behaving differently. And it's not doing what I want it to do. Okay? Yes?
The question relates to what was asked before. Are the human perturbations, they're also adaptive? I mean,
Yes.
the range of behaviors will change along the simulation, or it just...
It depends on you, but
It can
we
be...
can introduce adaptive behavior in an easier way, I think, than with other modeling techniques. Because you can use evolutionary algorithm that shift strategies towards a best outcome for that specific individual. You can introduce structured interactions and learning between people, or imitation and innovation. So yes, you can do that. And actually that's, I think, the big advantage to use these type of models, is that we can introduce feedbacks that allows us to maybe or maybe not understand better couple social projects.
But, I mean, maybe another way to ask it is if you redo a historical event of some
Yes.
culture vanishing or doing extinct, then what do you find? I mean, it seems like human societies are not patterned on human behavior.
No, it's not random, yes.
So in that case, what are you looking for? How do you validate?
You validate if the qualitative results of your model match the qualitative results of the curves of the historical data you have.
What do you tweak to get that?
You normally tweak certain parameters, like you have your variables and you have your functional responses. You tweak your parameters in such a way that the average of those runs you do, and normally you do some calculations, some simulations beforehand to understand how many runs you have to do before you have an average that is consistent, before it doesn't vary anymore, the average starts being always the same.
So there are no independent observations or opinions that are used. I mean, what is the constraint? Just one?
It depends on, again, because it's very flexible, so you build it in the code. So if you have empirical data that constrains your parameter space, then you say that these parameters can sweep only from here to here, from A to B. They can't go over, they can't go under. So you have a constraint. And you can constrain all the parameters, and actually that's what we do. Because exploring the whole parameter space it's impossible. I mean, computationally, it requires basically a cluster for random simulation. It would be nice to have access to, but we don't. So, any other? Yes?
I was just going to make a comment about the nice thing about anti-base is that you can also explain like geographical patterns, for instance.
Yeah.
And they did this really nice little experiment with, well not an experiment, but a anti-base model with the decision, how the patterns of racial distribution existed. And it was based on, So it was basically based on two parameters, the number of people, the number of your neighbours that were coloured, if you're a white person, and they were basically able to recreate the spatial distribution, racial distribution patterns in the suburbs in America on the basis of these two decision variables, basically.
Yeah, basically one variable showed a huge self-segregation in Chicago. That's it.
Is that different than the Shelley model?
No, that is the
Shelley
Shelley model.
model, yeah.
Yeah, that was based on a check. Yeah. And then evaluating agent-based models is often very difficult. So, first of all, if data are available and we can compare our results of the simulations on average equal to those of the real world, or similar, at least qualitatively, does the process by which agent and environment interact corresponds to the one that actually happens? And is the model coded correctly? So that I'm confident that all my results are actually a result solely of the model assumptions and not of how I coded it or some inbuilt constraints, okay, that I didn't realize I put in. I make a very quick example in these. For example, NetLogo has a very nice, as you see, spatial interface. Now, if I change if the borders are actually borders, or if the borders are, I can go from left and enter to right, so if it's a torus or not, it might change the outcome of the model. So I need to be aware of that. If I'm aware of that, and then I'm confident that the model then